All right, I think we're going to go ahead and get started. So welcome everyone to Nano at Tech. Before I introduce today's speaker, just a reminder, our last seminar for the semester this spring room. And the speaker will be Dr. Ryan Diestelhorst, who's part of a startup company called OnScale. And I think he's going to talk a lot about how to create a company and work with a startup. And so that might be an interesting talk for a lot of people. So it's a real pleasure to welcome both to Nano at Tech, but also to Georgia Tech more in general, since he's still in his 6 month or so, roughly 6 months, or maybe a little more, 6, 7 months. Times at Georgia Tech, Professor Shimeng Yu. He got his bachelor's degree in microelectronics at Peking University, and then a master's and PhD in electrical engineering at Stanford. He spent about 5 years at Arizona State University as an assistant professor in electrical and computer engineering before coming to Georgia Tech just last August, where he's currently an associate professor also in electrical and computer engineering. He's won a number of awards, most notably a Ditra Young Investigator Award, an SF Career Award, an IEEE Early Career Award from the Electron Devices Society. And he's also a senior member of IEEE. So welcome, Shimeng, and I'll hand it over to you.
Thank you, David, for the introduction. So good afternoon, everyone. I'm Shimeng from ECE. So today is my great pleasure to be here to share some of our research progress in the field of the neuro-inspired computing with emerging nano devices. And in particular, we call it synaptic or neuronal devices. So I'm very happy to be part of the Georgia Tech and also part of the IEN community here. And my students are right now doing the training in the clean room. So today I'm going to discuss some of the research progresses in this field. And this is the outline of the talk. Firstly, I'd like to talk about where we started from the development of the non-volatile memory for the traditional memory applications. And then I will talk about how we move our research from the non-volatile memory to these synaptic or neuronal devices. So how this transition happened. And then in particular, we are going to talk about two kinds of devices to do the synaptic device engineering for the offline training and online training. So this is to accelerate the neural network algorithms using our devices. And then we will talk about the challenges in the design for a large-scale system. That is the bottleneck from the peripheral circuits design point of view. So we need an analog to digital converter to convert the signals from the synaptic array to the neuron circuits. So we need some interface to do this transition, and we propose another kind of new devices to do this conversion. And eventually we'll talk about our recent progresses to do the ferroelectric based synaptic devices, which show some advantages to achieve good accuracy for the training. And this is outline. So we will start from the background. So this is where I started my research. So in the past decade or so, the industry actually spent a lot of efforts to develop this emerging non-volatile memory for the next generation non-volatile memory. So today's non-volatile memory, the mainstream technology is the flash. And we use it every day for your, let's say, SSD, solid-state drive. But the flash has some limitations in the scaling, so that's why the industry proposed those candidates to eventually replace the flash. So here are those devices. Most of them are based on the two-terminal devices. And for example, here the first one is this MTJ-based Spintronic memory. So in these cases, two layers of the ferromagnetic materials are separated by an oxide tunnel barrier, and depends on the magnetic orientations. So the resistance across this tunnel barrier will be different. So this is the first type of the emerging memory. And second one is this phase changing memory. So in this case, we have the phase changing material typically based on the chalcogenide. And then the phase of this material will transition between a amorphous state and a crystalline phase. So then the resistance will change according to the phase. And third type of the memory is this R1 resistive random access memory. So in this case, we have some insulator, which we can form some filament in the insulator to form this conductive bridge between two electrodes. And then we can tune the conductivity of this oxide layer as well. So those are different mechanisms, but from the circuit point of view, you can always abstract those devices as two-terminal resistor, but with the variable resistance. So depending on the voltage or the current pulses you apply to this device, you can tune the conductance of those devices. So for memory application, we just need 0 or 1 state of this device to represent the digital information. So this is the typical current versus voltage characteristics of this kind of R1 devices. So we can switch the device from the high-range state to the low-range state if we apply a large set voltage, or if we can reverse the state from the low-range state to the high-range state by applying elective reset voltage. So for the memory application, we just need to read the two states using a small voltage here. So you can think this is digital 0 or this is digital 1. So this is how we use for the memory application. But for today's talk, we are going to engineer this kind of device towards the synaptic devices that is useful for the neural network. So we are going to engineer multiple states of these devices based on some continuous states, analog states, instead of the digital states. So this is the target of our device engineering. But actually for the traditional memory application, in the past 10 years or so, the industry actually made a lot of progresses in this field. So this is a summary of the prototype chips published in the major circuit conferences, next ISCC or the VOSI symposium. So this is in terms of the capacity of that memory chip and the performance in terms of the write bandwidth or the read bandwidth. So you can see here the 3D NAND flash, which we use every day for the SSD, still dominates the density or the capacity. But the other emerging memories are catching up, like the R1 or phase change memory. But still, the density is lower than the 3D NAND. So that's why you don't see it on the market yet. But in terms of the performance, those devices generally outperform the flash by 10x in terms of the write bandwidth and the read bandwidth. So those are the emerging technologies here. So this is for the traditional memory application. And here are some prototype chips from different companies. So if we look at the traditional computing system, so this is the typical memory hierarchy we have in the system. So at the very top, we have the processor, which will do the computation. And then we have different levels of memories, depending on the access speed and the capacity. So to the very top, we have the cache, and SRAM is typically used for the cache. And then we have the main memory, and DRAM is used for the main memory. And then we have the SSD, and today is made by the 3D NAND flash. So this is the conventional computing system. But here we are trying to look at the possible positions of the new technology, emerging technologies. And here are the best sweet spots for those emerging technologies. For example, the STT-MRAM, the Spintronic-based memory, is expected to replace the last level cache, and also the R1 or the phase change memory, and 3D version of that is expected to create a new layer between the main memory and SSD. So this is so-called storage class memory. And if you read the news from Intel and Micron, so recently they have their product made by the 3D X-point memory, so which is a good example of the storage class memory between the main memory and SSD. So those are the applications towards the traditional computing system. But here in today's talk, we are going to talk a completely different computing system that is more driven by the neuro-inspired computing. So this is a paradigm shift of the computing system from the traditional von Neumann architecture to the Neuro-Inspired architecture. So here, this is trying to emulate the biological neural network. So if you look at our biological neural network, we have the neurons and synapses. So the neurons are the computing units which will do the activation of the inputs. And then the synapses are collections between two neurons. So basically, the synapses will carry the weight between two neurons. So the strength of the synapses will be reflected by the conductance of that synapse. So if two neurons are connected to each other with stronger synapses, that means those two neurons are more connected. So this is a neural network biological model. And then mathematically, from the machine learning, deep learning community, we are trying to build the mathematical formulas for the neural network. And this is abstraction of the formulas. So basically, we will have the inputs. Those are the, let's say, the output from the previous layer's neuron. And then the weights, which are the strengths of those synapses. And then we will have this product between the input vector and the weight matrix. So we'll get the so-called weighted sum in this fashion. And then this weighted sum will apply to the next layer's neuron. And to go through this neuron activation function, typically it's a nonlinear function to do the transfer process from the input weighted sum to the output. So this is the mathematical description of the neural network. Of course, this is not one-to-one mapping from what happens in the biological system, but this is a high-level description how we interpret the biological processes using the mathematical formulas. So here, the target of our design is to develop this kind of new devices to emulate the key components of this neuro-inspired computing system. That is the synapse and the neuron. So if we have those devices available, then we can build this kind of neuro-inspired architecture with distributed computation. So in this case, the memory war problem between the processor and the memory will not exist, because in the traditional von Neumann architecture, when we fetch the data from the memory to the processor, we will always go through this data bus. And because of the workloads like the machine learning, like image recognition, the workloads are very memory intensive. So here the data bus will become the bottleneck of the whole system. And in the neuro-inspired architecture, because we distribute the computations into multiple cores of the neurons and synapses, so this traffic jam will be eliminated. So this is basically this is a motivation of us to do this kind of device engineering to create new devices for the neurons or the synapses. So here again, the neurons are the computing units, and synapses are the memory components of this system. So this is a high-level picture of what we are doing right now. But in terms of the how we actually process the data, this is a slide for the crossbar architecture to accelerate the weighted sum and weight update process in the neural network. So here, the key idea is that if we can build a crossbar array like this with the horizontal rows and the vertical columns, and each cross point will have this little resistor we presented earlier. So this resistor will carry the weights of the neural network. So the idea is to map this kind of neural network. And let's say here are two layers of the network. We have the input neuron, output neuron, and then we have the fully connected synapses between those two layers of neurons. And the key idea is to map this kind of neural network model to this kind of physical layer of the hardware. And here, the input signals are going to be encoded as voltage to the crossbar array. And then the conductance, the weight matrix will be encoded as the conductance of those resistors here. So here, essentially, when we do the weighted sum operation in the mathematics, so here the input x will be encoded as voltage. And this voltage will be multiplied by the conductance, which is proportional to the weight, W, in the network. So we will get a weighted sum along the column because we are going to sum up the current from the column. So each voltage multiplication by the conductance will get a dot product of the current. And this current is going to be summed up along the column. So this is equivalent as the neural network is doing, because here mathematically we will have the matrix W and the input vector, and then we will get this dot product between the weight matrix and the input vector. So in devices, we are going to have the conductance as a matrix, and then the voltage input vector. So we will get this weighted sum. And then along the column, we are going to sum up the current. So those are equivalent processes between the mathematical formula and the hardware. So essentially here, we are going to use the Kirchhoff law to do the computation. So this is more like an analog computation, because all the signals here are analog in the nature. So this is what we can do to accelerate the weighted sum process, because if we apply the voltages in parallel, then we can get the current in parallel as well. So we don't need to do this sequential product between the input and the weight elements. We can do them in parallel fashion. So this is how we accelerate the process, by doing this analog computation within this crossbar array. And here, again, the key component of this crossbar array will be this little resistor, and we call it synaptic devices. And we are going to engineer those non-volatile memories we mentioned earlier, like the resistive random access memory, R1, to be the synaptic devices. And then at the end of the column, we are going to get the analog summation from those multiple devices. So we need to convert this analog output to some digital values, and then we're going to design a new device to do this job. So essentially, this is the job of the input stage of the neuron, because your neuron is to get the summation from the synaptic array and then convert that to the activation. So we're going to design a neuron to do this conversion as well. So this is a crossbar array we are going to build in this program. And in terms of this little resistor in the crossbar array, so those are the candidates, synaptic device candidates. So to implement this variable resistance of the synaptic devices, those are the candidates. And first two are based on the R1 devices, but the first one is filamentary. So in this case, we are going to create the filament in some oxide material. So the filament will carry the current. So we can tune the strength of the filament to tune the conductance of the device. And second one is non-filamentary R1. In this case, we don't create this filament, but we can control the density of the defects or the oxygen vacancies of the oxide to tune the conductance as well. So those two are based on the R1 devices. And third one is based on the phase change memory. So in this case, again, we have the phase change material based on the chalcogenide. But we can tune the volume of this amorphous region to represent the value of the weight. So this is another way to do the synaptic devices. And lastly, we can use this emerging ferroelectric field effect transistor to tune the domains in the gate dielectric, the ferroelectric domains. We can flip the domains. So equivalently, we can tune the threshold voltage of this transistor. So we can also have multiple states in the devices. So no matter which technology we are going to use, the key idea is to tune those devices into multiple conductance states or the variable resistance states. So we can represent the multiple weight values into a single devices. So this essentially is to develop analog memory instead of the digital memory 0 and 1. And here is a wish list of these synaptic devices. What are the ideal targets we want to engineer for? So of course, we want a small devices, let's say less than 10 nanometer in the scale, because eventually when we integrate large scale system, we need the density. And the programming voltage, that is the voltage we apply to change the conductance state of the device. And of course, we want small voltage, like 1 volt, to be compatible with the CMOS peripheral circuits. And then the number of states, how many states we need on each device. Here, just an example, larger than 100 states. And this is actually, it depends on the applications. Some applications may need even larger number of states. Some simple applications may just need a few states. So this totally depends on the applications. And the energy consumption, of course, we want small energy. And this is an example, like 10 femtojoule per programming pulse. This is actually equivalent to the biologic synapse to generate 1 spike. So this energy consumption is from the biologic synapse. And then dynamic range means on-off ratio. What is the ratio of the maximum conductance over the minimal conductance? And here we want to be as large as possible to represent a wide range of the weights. And then retention and endurance means the reliability. So retention means how long you can maintain the states after you program the device. And this is 10 years. This is as good as a non-volatile memory. So this is used for the offline training. I will talk about what is offline and online training later. So in the offline training, the main operation mode is to read the conductance after you program. So you don't need to reprogram. So that means your state needs to be stable over time. And then endurance means how many cycles you can program the device. And this is critical for the online training because you need to frequently update the weights. And here, for example, 10 to the power 6 cycles are needed. Of course, all of those numbers depends on the actual application, whether it's simple image recognition or video processing. So those values will vary, depends on the application. So then next we are going to talk about some of the device characteristics of this resistive memory-based devices. So here, firstly, for the offline training, which means the weights of the network are predefined by the software training. And in this case, we just need to do one-time programming of the weights to your hardware. And in this particular case, we use this half-link oxide-based RN devices to do this job. Because in this device, this is current versus voltage. And we can say that in the reset process, when you change the conductance from high to low, we can have continuous multiple states here. So we are going to use this region to generate multiple states. So this is good for the offline training, because after the training is done, we only do the inference of the network. But if we want to do the online training, that means we are going to update the weights on the devices directly. Then that means we need to increase and decrease the conductance very smoothly. So in this case, we have to have this both gradual set and reset behavior. That means we can achieve multiple states in both sets and reset processes. So this is good for the online training. I will go to this point later. Let's look at the offline training first. So in the offline training, the target is to program the device to some specific predefined states. So those states are predefined by the software training. And here in the devices, for example, we predefine those targets. For example, those conductance to be 50 microsiemens, or 10, or 5, or 1. So to achieve those levels, we develop the programming protocol like this. I will skip the details. But the key idea is to apply a pulse train with varying pulse amplitudes to converge the conductance of this device to the predefined target with some criterion, let's say 10% within the criterion. And then after 20 or 30 pulses, we can always converge the conductance to be this 50 micron Siemens. And after that, if we don't program it, those states will maintain over time. So this is good for the offline because your weights are predefined by the software training. And then after you program the device to be those conductances, you only read the conductances. So you want the conductances to be stable over time. So this device is capable of this multi-level programming, and this is good for the offline training. So with this kind of device, we actually implement a very small scale crossbar array. As we mentioned earlier, our target is to build this kind of resistor network in this crossbar fashion. So here in the university clean room, when I was at ASU before, we made this kind of 12 by 12 crossbar array. So this is the image of this crossbar array under the microscope. And here we have the probe card system to test this array. This is the setup in the probe station. So here the key idea is to implement a convolution kernel in this kind of crossbar array. And for example, here the convolution is the first step to process this image. For example, this handwritten digits. And then we have, for example, 3 by 3 kernel. And this kernel is to scan over this image to get the feature of this image from, for example, the edges from the image. So here the idea is to use this kind of crossbar array to do this processing. So this at each cross point, we have this half-linear oxide devices, as I showed in the previous slide. So here the idea is to do the offline training, predefine the conductance states, and then we program individual devices to be proportional to the conductance of the individual devices to be proportional to the weights as we predefined in the software. So here we map this kernel into 2 columns of this crossbar array, and then we will scan over the image. That means we are going to use the voltages to represent the pixel values of this image, and we will apply those voltages in parallel to the crossbar array, and then we will read out the current from the column. So this current will be the product between the input image and the kernel. So this is how we do this processing in parallel. And this is the results from this kind of experiments. So here, for example, we want to process this image of a dog. And then we have the small kernels, like 3 by 3. We are going to scan over the image. And then this is the simulation results for the edge detector kind of kernel. We program the kernel to be edge detection. So this is the simulation results. And then this is the measurement results from the crossbar array. So each pixel here is the current we measured from the column. So this current is proportional to the convolution results between the input image and that kernel we pre-programmed to the crossbar array. So we are going to use this anode current to represent the computation results between the input image and the kernel. So we have very close one-to-one mapping between the simulation results and the experimental results. So this is the idea to use this crossbar array to do the computation. Of course, this is a very toy model, like, only like 12 by 12 crossbar array, and we can only do this small kind of data set. So imagine we can build a large system with multiple layers, then we can actually process more complicated images and then extract more complicated features. So in this case, this feature is just the edge detection. So maybe we can construct larger systems to process more complicated images in the future. So this is the demo for that offline training. But for online training, the story is a little bit different. So for the online training, we are going to tune the conductance during the runtime or on the fly when you update the weights in the network. So there's no software training in this case. In this case, the training happens on the hardware. So in this case, that means we have to tune the conductance of those crossbar array very frequently. So in this case, we have to make sure the conductance can be tuned by the programming pulses in a very smooth fashion. So in this particular case, we collaborate with this group from Taiwan. So we have the two kinds of oxide layer, and in this case, we can modulate the density of the vacancies in one of the layer to tune the conductance of this device. So here is the conductance as a function of the programming pulses. So in this case, we only have a 2x2, very small array, but the idea is that we want to tune the conductance of those 4 devices simultaneously. So how do we achieve that? So we have to develop a programming protocol here. For example, if we want to tune the device's conductance according to the backpropagation rule, which says that the change of the conductance is proportional to the value of the row input Z and the column input R. So then we have to encode the Z value to be the duty cycle of this time window, and encode the R value to be the number of pulses in this time window. So when the Z value and R value, or let's say the Z pulse or the R pulse, overlap with each other, effectively we are going to have the voltage applied to the devices to tune the conductance. So here, for example, if the Z1 times R1, the first device, if the value is 16, we are going to update the devices by 16 steps. So that means the conductance will be tuned by 16 steps. And the second device here, if the Z1 times R2, the value is 8, we are going to update 8 steps. So in principle, we can update all the devices' conductance in one shot if we design the programming voltage proportional to the Z value and R value. So this is the concept to do the online training. That means we tune the conductance on the fly, on the hardware. And this is just a simple demo for a small scale array. We will face challenges when we scale up the system if we want to update all the cells' conductance at the same time. And one of the challenges is to get the continuous state or the conductance as a function of the programming pulse. And we have to make sure that the programming pulse is fast enough. So here we have another collaborative work with this Tsinghua group to basically engineer the half oxide with additional layer, capping layer, to make this conductance change as a function of the pulse number to be continuous and in analog fashion with fast programming pulse, like 50 nanoseconds. So this is ongoing work of our research group. So in the next, I will talk about some of the challenges in the peripheral circuits design. So far, we only focus on the resistors within the array. But after we get the current from the column, previously we used equipment to read out that current as we demonstrated in that crossbar array. But actually, when we think about the integrated system, we have to use peripheral circuits to do this job. And the idea is to convert the analog current to the digital output. So essentially, it's like ADC circuit design. And of course, we can use CMOS transistors to do this job. So this is one of the examples of this kind of ADC circuit. We can integrate this current on a capacitor, and then this current is going to charge this capacitor. And then we design some amplifier here to have some predefined threshold voltage. If the voltage on this capacitor is larger than the threshold, we are going to discharge this capacitor. So essentially, we are going to charge and discharge this capacitor depending on the input current strength. And within this time window, if we have more current, we are going to have faster charging and discharging process, so we can get more pulses at the end of at the output from these circuits. So for example, here, this is a SPICE simulation. If we have 6 micron input current as output of these circuits, we are going to generate 6 pulses. So if it's 1 micron, then output is 1 pulse. So this essentially does the job of ADC, and this is the input stage of the neuron. But the challenge here in the design is that we have so many transistors within one neuron node. And if you look at the crossbar array, actually the pitch from column to column is very small. And you cannot fit in this kind of large circuitry here. That means multiple columns have to share one circuit. So we have to use 10 multiplexing to read out all the columns, because we have to share this circuit among multiple columns. So this actually will reduce our parallelism, because ideally we want to read out all the columns at the same time. Because of this large circuitry, we have to slow down. So this is undesired. To overcome this problem, we propose this new device called oscillation neuron to replace this kind of circuitry with a single device. So this is our proposal. Here, the key component will be some threshold switch devices. So in particular, we use this niobium oxide devices, and which has this kind of threshold switching behavior. So this is niobium oxide, and this current versus voltage, and this device will turn on above the threshold voltage, and will spontaneously turn off below the hold voltage. So it's a switch, it's not memory, because it cannot memorize the states. But we have the hysteresis between the turn on and turn off transitions. So we have different voltages between the turn on and turn off transition. So if we have this kind of device, and then we integrate that device at the end of the column, then something interesting will happen. So this is because this is think about this is the equivalent resistance from this column, and then this is the voltage divider. And initially, if this niobium oxide device is in the off state, so that means resistance is high. So when you apply voltage from the top, most of the voltage will drop on this NBO niobium oxide devices. So that means this voltage is larger than the threshold voltage. So this device will turn on. But after the device turns on, then the resistance of this device decreases. So this, according to this voltage divider, then the voltage on these devices will become very small. So that means this voltage is smaller than this hold voltage. The device will turn off. So that means this device will spontaneously switch between on and off, and we call it oscillation. So this is experimental measurement results. If we apply voltages from the top, this is done by the circuit board. We have individual devices and then discrete resistor on the circuit board, and then we wire bond the the resistor to the device, and we tune the discrete resistors resistance, and then this is what we monitored from this node through the oscilloscope. So you can see that by changing the resistance here, we can tune the oscillation frequency. So this is proportional, because essentially the frequency is dominated by the RC time constant of this setup. So this is exactly what we emulate the neuron function, because if you look at this results, essentially here this node is doing this charging and discharging, and that is the same job as this circuit is doing, as we show in the previous slide. This circuit actually is doing the charging and discharging on this node, and then this circuit will convert the signal to the real-to-real signal after the inverter. So here, similarly, we should have another inverter to clean up the signal from real to real. So that means we can reduce most of the transistors here. So this is done in the circuit board, and next we are going to integrate this device to the crossbar array. So this is the fabrication steps, And I will skip the details, but the idea is to integrate this kind of neuron to the crossbar array on chip. So here we have first deposit the bottom electrode. This is one column of the array. And then we deposit a hafnium oxide as the synaptic devices. And then we build the middle electrode perpendicular to the horizontal electrodes. And then as edge of the array, we will deposit the niobium oxide material. And then this is just the one column of the crossbar array with the integrated synapses and the neurons. So this is the fabrication steps. And here is the fabricated array that integrates both synapses and the neurons. So here are zooming images. And for the synapses, those are the typical IV characteristics of those devices. And then the neurons will have this kind of threshold switching behavior between, let's say, threshold voltage and hold voltage. So in the next, we are going to use this kind of crossbar array to do some computation. So here, because we have one column of the array, so we are going to examine the oscillation frequency as input, as a function of the input. So here, for example, we have a different input vector with only one row turned on or multiple rows turned on. So here we have this kind of setup. We have an oscilloscope to monitor this voltage. And here, for example, this first row is we have only one input to the row. And then this is the oscillation behavior. And if we have two rows turned on, we are going to kind of double the oscillation frequency. If we have three rows turned on, then we can going to triple the oscillation frequency. So this is to use this oscillation frequency to actually convert the current to the digital output. Also, we examined the frequency as a function of the number of the resistive memories that are turned on in parallel. And here are some details. Due to the time limit, I will skip that. So this is what the ongoing efforts we are doing right now to integrate this crossbar array with the neuron devices. So eventually we will have this neural network based on the resistive synapses and the threshold switching neurons. So this is the recent results we have. And in the last section of this talk, I'm going to talk about the ferroelectric transistor-based analog synapses. So this is a new research we are going to pursue in the next. So this is under this SRC JUMP program with Professor Sumandata from Notre Dame. And the key idea here is that in the recent years, we found that if we have the hafnium oxide in the gate dielectric, if we dope the hafnium oxide with appropriate dopant like zirconium, then after the post-annealing, this HZO, hafnium zirconium oxide layer, will become ferroelectric. And this process is very compatible with the CMOS fabrication because nowadays, for the advanced transistors, this high-K metal gate is used. Essentially, it's the same material. The only difference is here is that here this material needs to go through the post-annealing process to have the crystallized phase, and which can show this ferroelectric behavior. In the conventional CMOS transistor we have today, this gate oxide is amorphous state. So that's the only difference here. So then if we can have this kind of ferroelectric gate dielectric, we can tune the polarization states of this material by applying gate voltage, gate pulses. And because of there are multiple domains within this thin film, we can tune the number of domains that are pointing up or pointing down, which will effectively tune the threshold voltage of the transistor. So if at a fixed gate read voltage, we can get multiple conductance states. So here, this is like 3 terminal devices. The programming is to apply the voltage to the gate, but the read is to read the channel conductance from source and the drain. So the write and the read paths are decoupled in these 3 terminal synaptic devices. So here are some results from Suman's group, and we can tune the device conductance into multiple states, up to 32 states, by this kind of non-identical programming scheme. And here are the drain current versus the gate voltage. Essentially, we tune the threshold voltage of these devices by applying the gate voltage to the ferroelectric transistor. So the job for us is to benchmark what device characteristics are needed for the neural network training process. So here we have some benchmark results of different kinds of devices. Firstly, this filamentary iron with this kind of conductance versus programming pulse behavior, very nonlinear and asymmetric. So in this case, the accuracy will not be good, even for the MNIST handwritten digits recognition, so only like 40%. So the key challenge is the weight update behavior is nonlinear. So ideally, in the software, we want this kind of linear update. That means when you increase the conductance or decrease the conductance, you will have the linear and symmetric steps instead of these nonlinear steps. So to improve this, we can engineer the devices. For example, with this interfacial engineering of the RN, we can improve that. But still, the accuracy is not very good because we still have a little bit nonlinearity and asymmetry. So with these ferroelectric devices from Suman's group, we can achieve this kind of symmetric update, but still it's nonlinear. So our accuracy is boosted to 90%. But we know that from the software training point of view, 90% is not good, because easily today for the handwritten digits, we can achieve like 98 or 99% of accuracy by the software. So in order for the hardware to match that kind of accuracy, so here we propose this 2-transistor, 1 FE-FET synaptic cell to achieve this very linear and symmetric weight update behavior. So in this case, we can achieve like 97% of the accuracy and using very fast programming pulses. So this is the state of the art in terms of the hardware implementations of the neural network accuracy. So in the next, I will quickly go through the design of this 2-transistor, 1 FE-FET synaptic cell. So in this case, we realize to implement this network, we cannot just use one single devices in order to achieve good accuracy. So we add 2 additional transistors to 1 synapse. And the idea is motivated by this hybrid precision requirement for training and inference. So here we see that for the training, that means we have to tune the weights of the network. That means we have to get high accuracy by using high precision of the weights. Here from the software simulation, we realize at least 6 bits are needed for the high accuracy. So 6 bits means 64 levels of the conductance. So it's quite challenging to get 64 levels of conductance within one device. But for the inference, that means after the training is done, we only do the read operation of the device. Then actually 1 or 2 bits is sufficient for the inference. So here the key idea of this design is to split the weights precision into 2 parts. One is the most significant bits, MSB. One is least significant bits, LSB. So for example, 6 bits of the weight is represented by 2 bits in the non-volatile memory and 4 bits in some volatile memory, for example, a capacitor. So this is a key motivation of this design. And to use this concept, we propose this 2-transistor, 1 FE-FET design. And here, the MSBs are encoded as the threshold voltage states of this FE-FET devices. And LSBs are encoded as the voltage to the gate of this FE-FET. So for the LSBs, we are going to charge and discharge this load voltage by the pull-up transistor and pull-down transistor. So this charging and discharging can be fast and symmetric. And after the LSB are updated, then we can transfer the weights to the MSB. So that means we can tune the threshold voltage of this FE-FET to store the most important information into the MSBs. So this is like a volatile memory because this is a gate capacitor. This is like a capacitor. But at the same time, this gate is a ferroelectric gate. That means you can program the gate to be different polarization states. You can memorize the non-volatile information into the gate material as well. So this gate is both volatile memory because it's capacitor and non-volatile memory because you can encode the information into the polarization states. So due to the time limit, I will skip the details of the design. But what I want to show here is if you do this way, then the conductance versus the programming pulses can be very symmetric and linear. So this is what we want for the devices. So with this kind of setup, then if we evaluate this kind of device, of course we don't have the system right now, but if we use this device to build a system, then for example, to build up this kind of neural network for the MList handwritten digits recognition, then this is the accuracy, training accuracy if we use this kind of devices. So basically what we do here is to modify the software simulation in the TensorFlow framework, but incorporate the device model like this. That means we modify the weight update step in the algorithm to incorporate the device model like this. And then we consider the device variation and nonlinearity in the devices. Then eventually we can get very close to the software accuracy. For example, software ideally 98.5%. And if we use this kind of devices, then we can get 98.3% accuracy. So this is for a small data set. And also we can do a larger data set, like the CIFAR-10 data set for this kind of image recognition. And the software can do 90%, and we can do like 88%. So still we see a little bit of degradation from the software due to the variation and limited precision of the devices. But this is kind of close to the software. Okay, so I'd like to summarize my talk. So basically in this talk, we discuss about the recent progress of the Neuro-Inspired Computing. And to achieve this large-scale system, we have to develop the compact devices to emulate the key functions of the network that are the neurons and synapses. So for the synapses, we use this resistive random access memory, and that can have multi-level states. So for the offline training, we use write and verify programming protocol to program the device into multi-level states. And the state will carry the weight information. But still, we realize that device engineering is needed to improve the anak tuning behavior for online training. So for the neuron, we realize that the neurons are placed at the edge of the crossbar array. And then we have to make the neuron to be very compact to solve the bottleneck of the ADC circuitry. So in this case, we propose this threshold switch devices, for example, the niobium oxide, to behave like an oscillation neuron, which translates the current from the crossbar array to the oscillation frequency by a single device. So the future work is to improve the endurance of that device, because we have to oscillate many cycles. We have to make sure the device have enough lifetime. And at the very end, we talk about the ferroelectric-based synaptic devices, because we think those ferroelectric devices may offer some advantages because they decouple the write and read paths. And also we propose this actually 2 transistor, 1 FE-FET synaptic cell to combine the advantage of the volatile memory and non-volatile memory. So we can achieve very good accuracy for the training, even for large-scale data set. So this is the summary of this talk. I'd like to thank all the students involved in this research and my collaborators and also the sponsors of the research. So I can take some quick questions. Thank you. Mm-hmm. You mean how to make the single half-line oxide-based device both gradual set and reset? Correct. So this, that's a very hard question. So I think single half-line oxide devices are very difficult to achieve both set and gradual set and reset because in the set process, when you create the filament, there's a strong positive feedback between the filament growth speed and the electric field and temperature. So it's very hard to control. That's why we have to engineer this device. For example, I didn't have time to talk about this concept. So we have to engineer the device by adding maybe some additional layer, like bilayer oxide structure, to avoid this kind of strong filament formation. So if you have single half-line oxide layer, it's very challenging. But if you can engineer the device structure by adding additional layer of oxide, which in this case, we use like tantalum oxide, like bilayer structure. So the tantalum oxide can be a buffer layer. And then the tantalum oxide, if it can be a good heat thermal enhanced layer, which can help the system to generate weak filaments instead of strong filaments. Then there is a possibility to achieve gradual set as well. But still it's quite challenging from the device engineering point of view. We can discuss offline, but there are some possibilities, but not very easy, I would say. Single layer half-line oxide, I don't think is possible, but with some modification of the device structure, there are some possibilities. Yeah.
Just by changing the substrate, like modifying the thermal bonding material, we kind of see gradual, but like there is also limitations to the measurement. Like we cannot apply higher voltages.
Okay, we can discuss, yeah, afterwards.
And for one more question, if there's anybody got something pressing.
Oh, slide 14.
Yeah. You want me to go to that?
Yeah, can you explain how you program it so that you detect the edge?
This one?
Yeah.
So maybe we'll go previous slide. So this one is offline training. That means the kernel are predefined by software training. That means those values of the conductance are predefined. So what we do here is to have a 3x3 kernel like this, and then we unroll the kernel to be line elements along the column. And then the kernel value are programmed as a conductance of this device. So then we have this 3x3 kernel. It's like a window to the input image. Then we are going to scan over the image. That means let's say the first 3x3 line pixels value will be encoded as a voltage applied to the row. And then this voltage will multiply by the conductance, which is the kernel. And then we can get the weighted sum from the input image pixel value and then the kernel or the weights, which in this case is the conductance. The input is voltage. Voltage times conductance, we get current. And we sum up the current. So this current will be in this convolution results between the input window and the kernel. And then if we scan over this image, then we will get the edges. Because mathematically, when you do that in software, this is what you will get between that input window and the kernel, which is predefined by the software, and you will get this kind of value of the convolution. And this is the current we measured, so those can match.
Okay, I think in light of the time, let's thank you one more time.
Thank you.